Okay, another practice problem. We're going to do 9.10. It states here a 14-foot long simply supported timber beam carries a 6-foot concentrated load at midspan. Cross-sectional dimensions are shown. It says here we want to find at section A, tack A. So that's going to be right here, section AA. We want to look and determine the magnitude of the shear stress at point H, magnitude of the shear stress at point K. Then we want to determine the maximum horizontal shear stress that occurs anywhere along the member, and then determine the maximum tension bending stress that occurs anywhere along the member. So the first thing that we want to do is just quickly draw up our simply supported beam. We have 6 kips working here, right in the center, which means we're going to have 3 kips acting at each reaction, and this is 7 feet. So drawing our shear and moment diagrams, we're going to have our shear and then our moment. So shear is going to be 3 kips up, and then over to this load. It'll go shoot down to -3 kips, come over here, and then come back up. And so if that's our in kips, V in kips, this is 3, 3, -3, -3. So 3 times 7 is 21. So our moment in kip feet is going to go from 0 to our maximum right in the center. So we determined this is 21. And since we were asked to find the point at AA, right, AA, which we want to know the shear at that point and then the moment at that point. So this is 3 kips, and then 21 divided by 7 is 3, and then the distance between these 2 points, that's 3 feet, so 3 times 3 is 9. That's 9. It's our moment right there. So now what we want to do is look at our member here, and the moment of inertia for this, our I value, is going to be our base multiplied to height cubed over 12, which is going to be 6 multiplied to 15 cubed over 12, and that is 1,687.5 inches to the 4th. Okay, and so for the first part, part A, it asks for the shear stress at point H, right? So at point H. So point H is right here, and that's 3 inches from our upper point, right? If we draw, I'm going to redraw this here and say point H is here. This distance is 3 inches. Our centroid is here, and this total distance from here to here is 15 divided by 2, which is 7.5. So this distance here is 6 inches. So Q is going to equal the area that we're interested in, which is going to be this area here, right? So 6 inches multiplied to 3 inches. And then we have to, this is our area, right? Because Q equals area multiplied to y sub I. But what's y sub I? Y sub I is going to be multiplied, or is the distance from the centroid of the whole member to the centroid of the area that we're looking at, okay? And so that's halfway in this rectangle is 1.5 from the outermost edge. So 7.5 minus 1.5 is 6. So y sub I is 6. So Q for this section then equals 108 inches cubed. Okay? So our shear stress is going to be tau equals our shear, Q, divided by I multiplied to the thickness. So our shear, which we determined up here, is 3 kips. So 3 kips multiplied to 108 inches cubed divided by 1,687.5 inches to the 4th multiplied to our thickness, which is 6 inches. And this should equal, it's going to equal a small number. So let's multiply this to 1,000 pounds per 1 kip. And that'll look better. Okay, so then we get 32, and we'll just round 0.0 pounds per inches squared, or this will equal just 32.0 psi. And this is for the shear stress at point H. Okay? So the next part of the problem asked for point K, right? So at point K, and I'll draw another rectangle to try and get, so you can see where we're going to find our, our Q value. If this is the centroid, and this distance here is 7.5, and then if this is our K, which is 1 inch from the outermost edge, then our area in question, right? So Q equals 6 multiplied to 1, and if it's 1 inch halfway through there, our y sub I from the centroid of the whole member to the centroid of the area that we're analyzing is going to be 7 inches. So we'll say 7. So Q for this one is going to be 42 inches cubed. So our shear stress is going to equal V Q over IT. Same shear, right, as before in the last problem. So we'll say 3 kips multiplied to, we'll do our unit conversion, pounds per 1 kip, multiplied to our Q, which is 42 inches cubed, divided by our 1,687.5 inches to the 4th, multiplied to a thickness, which is 6 inches. And so the shear stress at point K, you should get 12.44, we'll just say PSI, pounds per square inch. Okay. So the next part of the problem asks for maximum shear stress at any location, right? So max shear stress at any location, right? Then that's going to be, the shear is pretty much 3. The magnitude's 3, be it negative or positive, depending on where we are. So the maximum shear stress, we can just say for anywhere at the member, right? We need to determine what Q is. So if this is 7.5, what's the maximum shear stress? Well, we're going to analyze our section is going to be this entire area. Okay? So it's going to be Q equals 6 multiplied to 7.5, which is our area, multiplied to 7.5 divided by 2 is 3.75. So Q for this one would be 168.75 75 inches to the third, inches cubed. So our shear stress is going to be tau equals VQ over IT, which is going to be 3,000 pounds multiplied to 168.75 inches cubed divided by the same moment of inertia, 168.75 inches to the fourth multiplied to 6 inches. You should get a shear stress of 50, rounding, 50.0 pounds per square inch. Okay? So the maximum bending stress, the last part of this question, asks for the maximum bending stress at any location on this beam. So we already determined any location on this beam, right? So the maximum bending stress, which is bending, is going to equal my over I, right? So our distance, our y value is going to be our 7.5. So we'll say we have our moment, which is 21 kip feet, right? Which we determined in the first part of the problem. And we'll change that units to inches per 1 foot. And then our distance is 7.5 inches divided by our moment of inertia, which is 168.7.5 inches to the fourth. So our bending stress should equal 1,000 or 1.12 kips per square inch, which is also equals 1,120 psi. Now this is going to be either in tension or compression depending on where you are in the beam.